Find somewhere comfortable. You don't need to sit up straight or hold anything in your mind. You don't need to remember a single word of what follows. Just let the ideas arrive the way sounds do when you're half asleep, present for a moment, then drifting on without you. Tonight we're going underground. Beneath a quiet stretch of countryside on the French-Swiss border, beneath farmers' fields and small roads and the roots of old trees, something enormous is running in the dark. A machine, patient and cold and precise beyond anything you could hold in your imagination. It has been running for years, asking the same ancient question over and over in the only language the universe seems willing to answer. We're going to go there together. Down into the tunnel, into the heart of the machine, and then further still, into the heart of the atom, and the heart of what the atom is made of, and the forces that hold all of it together, including you. You don't need to concentrate. You don't need to follow every detail. Just let the words wash through. Some of them will settle, some will dissolve before they land. Either way is fine. We're in no hurry tonight. Somewhere beneath the gentle hills between Geneva and the Jura Mountains, there is a tunnel. It is roughly circular. It runs for 27 kilometers, that's about 17 miles, bored through the rock and clay at a depth of around 100 meters, far enough underground that the surface world becomes entirely irrelevant. No weather reaches it. No traffic noise, no seasons, just the rock and the cold and the machine. This is the Large Hadron Collider, the LHC. It is the largest and most complex scientific instrument ever built by human beings, and yet the thing it is searching for, the fundamental nature of matter, is so small that the word small barely applies. The scales involved in this enterprise are so extreme in both directions, so vast at one end and so minute at the other, that the mind cannot really hold them simultaneously. So we take them one at a time, the way you'd explore a very large, very dark house with a small lamp. The tunnel itself was not built for the LHC. It was excavated in the 1980s for an earlier machine, and when that machine had finished its work, the LHC was installed in its place, a kind of inheritance, one generation of science handing something precious to the next. Walking the full circumference of the tunnel would take a healthy person roughly 5 or 6 hours. It curves so gently that if you stood at any point inside it and looked along the beam line, the walls would appear almost straight. The curvature is only apparent from above, from maps, from the scale of the thing seen whole. The temperature inside the LHC is one of the first things that catches you. Not the temperature of the tunnel itself, which is cool but ordinary. The temperature of the magnets that steer the beam. Those magnets are cooled to 1.9 Kelvin. To understand what that means, the Kelvin scale starts at absolute zero, the coldest temperature physically possible, the point at which all thermal motion ceases. 0 Kelvin is minus 273 degrees Celsius. Outer space, the vast empty regions between galaxies, sits at about 2.7 Kelvin, because even the darkness of the universe is warmed slightly by the faint afterglow of the Big Bang. The LHC's magnets are colder than that, colder than the space between stars. They represent some of the coldest large-scale volumes of matter anywhere in the observable universe, and they exist quietly beneath a field in Switzerland. Why so cold? Because the magnets that bend the proton beam are superconducting magnets. Superconductivity is a state that certain materials enter at extremely low temperatures in which their electrical resistance drops to exactly zero, not nearly zero, exactly zero. In an ordinary copper wire, electrons carrying current collide constantly with the atoms of the wire, losing energy as heat. That's why wires get warm. In a superconductor below its critical temperature, the electrons pair up and move in a coordinated quantum state, a state where they no longer scatter off atoms at all. Current flows without any loss. This matters enormously for the LHC because bending a beam of protons traveling at nearly the speed of light requires magnetic fields of extraordinary strength, around 8 Tesla, roughly 160,000 times stronger than Earth's own magnetic field. Generating that field with ordinary magnets would require so much electrical power and produce so much heat as to be entirely impractical. Superconducting magnets make it possible. The cold is not incidental. The cold is the whole point. There are 1,232 of these bending magnets arranged around the ring, each about 15 meters long, each a precise and patient piece of engineering. They are connected in a single continuous cryogenic system, a chain of extreme cold running all the way around the 27-kilometer loop, and threading through the bore of each magnet inside a pipe maintained at a vacuum more complete than anything found in the natural solar system are the protons. The protons come from hydrogen. Specifically, from a small bottle of hydrogen gas, a bottle no larger than a fire extinguisher that sits in a service area at CERN and is replaced only twice a year. Hydrogen is the simplest element. One proton, one electron, held together by electrical attraction. To liberate the proton, you simply strip the electron away with an electric field. What remains is a bare proton, a tiny nugget of positive charge ready to be pushed. And then the pushing begins. But before we follow that proton on its journey, before we watch it accelerate through the machine's successive stages, gaining energy, curving, narrowing into a beam so focused it could thread a needle, it is worth staying here a moment longer. People who have been inside the LHC tunnel during maintenance periods describe a particular quality to the experience. The scale is wrong in a way that takes time to adjust to. The beam pipe itself runs along one side, enclosed in the blue casing of the magnet system, and beside it runs a narrow walkway. The curve of the tunnel is so gentle you can see perhaps 100 meters ahead before the corridor bends out of sight, and then 100 meters more around the next arc, and so on, seemingly forever. The silence is heavy. There is a faint hum. Not loud, just present, the sound of systems running, of cooling circuits, of the building's own vast and patient breath. Standing there, it is possible to feel something that is difficult to articulate. It is not exactly awe at the machine, though the machine is extraordinary. It is more a feeling of proximity to a question. The question that human beings have been asking, in one form or another, for as long as there have been human beings. What is all of this made of? What is the ground beneath the ground? What is the smallest thing? The LHC is the most elaborate, most expensive, most precisely engineered attempt to answer that question that has ever existed, and its starting point is a bottle of hydrogen gas replaced twice a year whose protons supply everything. The largest machine in the world, fed by something you could hold in one hand. The protons, once freed from their electrons, are injected into a small linear accelerator, a straight section of machine, where they receive their first push. From there they pass into a series of progressively larger circular machines, each one handing them off to the next with greater energy, like a relay race run at ever-increasing speed. By the time they reach the main ring, they are already moving at a substantial fraction of the speed of light, and then the ring begins its work. There are two beams in the LHC. They travel in opposite directions, each one curling around the 27-kilometer loop, guided by those superconducting magnets. At 4 specific points around the ring, the beams are steered to cross each other, and in those crossing points, not all of them, the beams pass through each other like 2 clouds of smoke, and only occasionally does one proton actually strike another. But the beams are dense with protons, and they cross each other 40 million times per second, and so the collisions accumulate. Each one a tiny, violent, extraordinarily brief event in which the protons cease to be protons, and something else briefly takes their place. The precision required to make this happen is the kind that resists easy description. Engineers sometimes reach for an analogy. Imagine firing 2 needles from 10 kilometers apart, aimed at each other and making them meet in the middle. That is roughly the level of accuracy involved in steering two beams of protons through 27 kilometers of curved pipe until they intersect at a designated point with enough reliability to produce billions of useful collisions. It requires magnetic fields calibrated to extraordinary precision, beam positions monitored by instruments sensitive to movements smaller than a human hair, and a feedback system that is constantly correcting, adjusting, holding the beam true. All of this so that two protons can meet and in meeting reveal what they are made of. The tunnel is quiet now, in the dark beneath the fields. The magnets are cold. The beam is running. Something ancient and patient is happening down there, in the rock, in the silence, in the cold. And it has been happening in one form or another since the first person looked at a piece of matter and wondered what it truly was. To understand how a proton goes from the tip of a hydrogen bottle to 99.999999% at the speed of light, it helps to start with something very simple. A charged particle in an electric field feels a force. That's it. An electric field pushes positive charges in one direction and pulls them in another, and a proton, being a positive charge, can be nudged, shoved, and ultimately hurled by a sequence of carefully arranged electric fields. The first section of the journey is a linear accelerator, a straight tube perhaps 30 meters long, where the proton receives its initial acceleration. Electric fields along this tube push the proton forward, and by the time it exits, it is already moving at a significant speed, though still nowhere near what the main ring will eventually achieve. This is just the beginning, the first step of a relay that will pass the proton through several increasingly powerful machines before it reaches the main LHC ring. But a linear accelerator, however useful, has a fundamental limitation. To keep accelerating the particle, you need more and more length. The longest linear accelerator ever built for physics research at the SLAC National Accelerator Laboratory in California stretches for 3 kilometers and is one of the longest buildings on Earth. Even so, it could only push electrons to a fraction of the energy the LHC routinely achieves. To reach truly high energies, you need to push the particle again and again. And the way you do that without building an infinitely long straight line is to bend the particle's path into a circle so it passes through the accelerating sections repeatedly. This is the core idea behind a circular accelerator. And the thing that does the accelerating in the LHC, as in most modern machines, is not a simple static electric field, but something more elegant, a radio frequency cavity. Picture a metallic chamber, roughly cylindrical, perhaps the size of a large barrel, installed along the beam pipe. Inside this chamber, an oscillating electromagnetic field is maintained at a specific frequency, typically in the range of radio waves. The field inside the cavity alternates, positive, then negative, then positive again, cycling hundreds of millions of times per second. Now imagine a proton arriving at this cavity. If the timing is right, if the proton arrives at precisely the moment when the field inside is oriented to push it forward, the proton receives a kick of energy and exits the cavity moving faster than it entered. The cavity has, in effect, handed a packet of energy to the proton. The analogy that physicists sometimes reach for is an organ pipe. An organ pipe resonates at a particular frequency, sustaining a standing wave of sound within its length. An RF cavity does something similar with electromagnetic waves, sustaining a resonant pattern of electric and magnetic fields that can transfer energy with remarkable efficiency. The cavity is tuned so that its resonant frequency matches the arrival rate of the proton bunches. The protons arrive just as the field is in the right phase to accelerate them, and the geometry of the cavity is designed so that the field inside is always aligned with the direction of travel. One cavity provides a modest kick. The LHC has 16 of them arranged in groups, and a proton passes through them on every lap of the ring. Each pass adds a little more energy. Lap after lap, the energy accumulates. Over the course of several minutes, during which the proton completes millions of circuits, the energy grows from a few 100 million electron volts to several trillion. An electron volt, to give you a sense of scale, is the energy gained by a single electron moving across a 1-volt battery. A trillion electron volts is a tera-electron volt, or TeV. Each proton in the LHC beam eventually carries 6.5 tera-electron volts of energy, an amount that, while tiny on human scales, is extraordinary for a single subatomic particle, roughly equivalent to the kinetic energy of a flying mosquito compressed into something a billion times smaller. Now, as the proton gains energy, something must also change. The proton is circling a ring. For it to stay in that ring rather than flying off in a straight line, it must be constantly steered. Its path must be continuously curved. This is done by the superconducting bending magnets. A magnetic field exerts a force on a moving charged particle, perpendicular to its direction of travel, which is exactly what's needed to curve a path into a circle. But here is the subtlety. The faster the particle moves, and the more energy it carries, the harder it is to bend. A more energetic proton requires a stronger magnetic field to follow the same circular path. This means that as the RF cavities increase the proton's energy, the bending magnets must simultaneously increase their field strength in precise lockstep to keep the proton on track. A machine that operates this way, where the magnetic field and the particle energy are increased together in synchrony, is called a synchrotron. It is the defining principle of the LHC and of most large modern accelerators. The name captures the essential idea: synchronization. The magnets and the acceleration must always be matched. Too little magnetic field and the proton drifts outward, spiraling toward the wall. Too much field and it curves inward, spiraling the other way. Only when the two are precisely balanced does the proton continue its circular orbit, lap after lap, gaining energy, the magnetic field rising to meet it. You may be wondering why the protons travel in bunches rather than a continuous stream. The reason is directly tied to the RF cavities. The cavities accelerate a proton only when the proton arrives at the right moment in the oscillating field cycle. If a proton arrives slightly early, it receives a slightly smaller kick. If it arrives slightly late, it receives a slightly larger one. This turns out to be a natural stabilizing mechanism. Protons that drift ahead of the ideal timing get pushed back, and protons that fall behind get pushed forward. The result is that protons naturally cluster into groups, bunches, each one containing hundreds of billions of individual protons, with the protons within each bunch held in a stable formation by the rhythm of the field. The LHC typically runs with around 2,800 of these bunches in each beam, spaced around the ring like beads on a very fast necklace. Inside the beam pipe, where these bunches travel, the vacuum is extraordinary. The pressure is reduced to about 10 to the minus 13 of normal atmospheric pressure, roughly 100 times lower than the pressure on the surface of the moon, and far lower than anything naturally occurring in the inner solar system. Why? Because at the speeds the protons are traveling, even a collision with a single gas molecule would scatter them off course. The beam would dissolve. The vacuum is not a refinement. It is a prerequisite. And now we arrive at something that Einstein understood and that every particle accelerator in the world must reckon with. As a particle approaches the speed of light, something strange happens to the relationship between energy and speed. In everyday experience, if you double the energy you put into pushing something, you roughly double its speed. But at speeds close to the speed of light, this simple relationship breaks down. According to Einstein's special theory of relativity, as a particle moves faster, its effective mass, the resistance it offers to further acceleration, increases. Not its rest mass, the mass it would have if you weighed it sitting still. Its effective inertial mass, the mass that determines how hard it is to push. At 99% of the speed of light, the effective mass of a proton is about 7 times its rest mass. At 99.9%, it is about 22 times. At the speeds the LHC achieves 99.999999% of the speed of light, the proton's effective mass is approximately 7,000 times its rest mass. Each additional joule of energy you pour in accelerates the proton by a smaller and smaller amount. The speed asymptotically approaches the speed of light, but can never reach it. This is not a limitation of our technology. It is a feature of the universe. The speed of light is not a barrier that better engineering could one day overcome. It is the boundary of what is physically possible for anything with mass. This is why the LHC, despite its extraordinary energies, does not make protons travel at exactly the speed of light. It makes them travel so close to it that the difference is almost meaningless for practical purposes. The gap between their speed and the speed of light is less than 4 meters per second, but the gap is real and it is permanent. The energy that cannot be converted into speed goes instead into the proton's effective mass. And it is precisely that enormous effective mass, that concentrated relativistic energy, that becomes available for creating new particles when two protons collide. The protons circle the ring about 11,000 times per second. In a single second, a proton in the LHC travels a distance of roughly 300 million meters. It crosses the tunnel between France and Switzerland, not once, not 100 times, but hundreds of thousands of times in the time it takes you to draw a breath. And all of that motion, all of that energy is held in a pipe you could almost wrap your arms around, kept cold and focused and true by magnets cooled to a temperature the stars have never seen. There is something meditative in this, if you let it be. The proton going around and around, gaining a little more energy on each pass, patient as water finding its level. The machine breathing in synchrony with it, the magnetic fields rising steadily, the cavities pulsing. A rhythm built into the physics itself, sustained for hours at a time, until the beam is ready and the collisions can begin. The story of particle accelerators does not begin underground. It begins in small rooms, with modest equipment, and with people who were simply trying to understand something that had never been understood before. In the spring of 1932, in a laboratory in Cambridge, two young physicists performed an experiment that would later win them the Nobel Prize, though at the time it felt less like triumph than relief. John Cockcroft was a careful, methodical Englishman who had studied electrical engineering before turning to physics. Ernest Walton was an Irishman, quiet and precise, who had come to Cambridge on a research studentship. Together, under the supervision of Ernest Rutherford, who had himself discovered the atomic nucleus 2 decades earlier, they built a machine capable of accelerating protons to energies high enough to split an atomic nucleus. The machine they built was a voltage multiplier, a stack of capacitors and rectifiers that could be charged in parallel and discharged in series, generating a high voltage from a modest power supply. It was not elegant by modern standards. It filled a room. Its high-voltage terminals were enclosed in large metal cylinders to prevent sparking. The proton beam it produced was accelerated through a glass tube and directed at a thin target of lithium metal. And what happened when those protons struck? The lithium was something that had never been made to happen before by human hands. A lithium nucleus, which contains 3 protons and 4 neutrons, absorbed an incoming proton and promptly split into 2 helium nuclei, each flying apart with considerable energy. This was nuclear transmutation, one element becoming another, not through radioactive decay, which is spontaneous and uncontrolled, but through deliberate bombardment with an artificially accelerated particle. Walton, who was crouching inside a small lead-lined hut to shield himself from radiation while peering through a microscope at a zinc sulfide screen, was the first to see the flashes, tiny points of light, each marking the arrival of a helium nucleus. He called Cockcroft over. They looked at the screen together, and they understood what they were seeing. Rutherford, when he arrived, reportedly said something to the effect that they had split the atom, which was not quite right. They had split the nucleus, which is not the same thing as the atom. But the spirit of the remark was accurate. For the first time, the interior of the nucleus had been reached by artificial means. The energy released confirmed, for the first time in a laboratory, Einstein's relationship between mass and energy. The two helium nuclei together weighed slightly less than the original lithium nucleus, plus proton, and the missing mass had become kinetic energy, exactly as the theory predicted. It was a quiet, careful experiment in a Cambridge room, and it changed what physics knew it could do. While Cockcroft and Walton were building their voltage multiplier, a very different kind of mind was working on the same problem in California. Ernest Lawrence was an American physicist at Berkeley, enthusiastic, ambitious, and possessed of a particular gift for imagining things that did not yet exist. In 1929, while reading a paper by a Norwegian engineer named Rolf Weidery, Lawrence encountered an idea that stopped him. What if you could accelerate particles not by applying one very large voltage, but by applying a modest voltage repeatedly? What if the particle could be made to pass through the same accelerating gap over and over? Weidery had demonstrated a version of this in a straight line, but Lawrence saw something. Weidery had not pursued. If a magnetic field was applied perpendicular to the particle's motion, the particle would curve, and as the particle gained energy and moved faster, it would curve in a larger arc. In a uniform magnetic field, a particle naturally spirals outward as it gains energy, returning to the accelerating gap again and again, each time at a slightly larger radius. The path is a spiral. Lawrence sketched the idea on a piece of paper. The device would consist of two hollow semicircular metal chambers shaped like the letter D and so-called D-shaped electrodes, or Ds, placed face-to-face with a gap between them. An alternating electric field would be applied across the gap, timed to push the particle forward every time it crossed. A magnetic field perpendicular to the plane of the Ds would curve the path into a spiral. Each time the particle crossed the gap and received a kick of energy, it would swing out in a slightly larger arc until eventually it reached the outer edge of the device and could be extracted. The first cyclotron Lawrence built in 1930 was about the size of a dinner plate. It cost a few $100s in materials, much of it scrounged from the laboratory. It accelerated protons to about 80,000 electron volts, modest by any later standard, but proof that the principle worked. Within 2 years, he had built a larger version, and the cyclotron became the dominant tool of nuclear physics for the next 2 decades. Lawrence was awarded the Nobel Prize in 1939. The cyclotron was elegant, but it had a limit. As the proton spirals outward and gains energy, it moves faster, and the time it takes to complete each half circle begins to change. At relativistic speeds, speeds close to that of light, the increasing effective mass of the particle means it takes longer to curve around, and it falls out of synchrony with the alternating electric field. The cyclotron's fixed magnetic field and fixed frequency, which work beautifully at low energies, stop working when the particle becomes relativistic. This is not a flaw in Lawrence's design. It is a consequence of Einstein's physics, which no engineering can circumvent. The solution, developed in the late 1940s, was the synchrotron, the machine whose principle we described in the previous chapter, where both the magnetic field and the accelerating frequency are adjusted together as the particle gains energy, keeping it on a fixed circular orbit rather than allowing it to spiral. The synchrotron freed accelerators from the relativistic ceiling that limited the cyclotron, and it opened the door to the energies needed to probe the nucleus and eventually the particles inside it. Through the 1950s and into the 1960s, larger and larger synchrotrons were built, first in the United States, at Brookhaven in New York, at Berkeley in California, and then in Europe, where CERN, the European Organization for Nuclear Research, was founded in 1954 as a cooperative effort among 12 nations, a scientific institution built from the conviction that knowledge was worth sharing across borders. Each new machine reached higher energies, and each new energy threshold revealed particles that no one had predicted and no one quite knew what to do with. This is the part of the history that tends to be glossed over, but it is worth sitting with for a moment. The 1950s and 1960s were not a period of keen discovery leading smoothly to understanding. They were a period of bewilderment. Each new accelerator seemed to produce not answers but more particles. Particles with odd properties, particles that decayed in unexpected ways, particles that seemed to be related to each other, but whose relationship no one could articulate. By the early 1960s, the list of known subatomic particles had grown so long that it had acquired a half-joking name, the particle zoo. There were pions and kaons and eta mesons. There were lambdas and sigmas and x's. There were particles that existed for a billionth of a second and particles that existed for a billionth of a second. The proton and neutron, once thought to be fundamental, sat within this zoo looking less and less special. The theorists were struggling. The experimenters were producing data faster than anyone could make sense of it. And there was a growing suspicion, not yet confirmed, not yet proven, but present in the conversations of physicists, that all of these particles were not fundamental at all, that they were combinations of something smaller, that the zoo had a hidden order, and that order lay one level deeper than anyone had yet been able to see. To see that level deeper, you needed more energy, and to have more energy, you needed bigger machines. The history of particle physics in this period is not a story of triumph following triumph. It is a story of patient, sometimes frustrated accumulation. Each machine building on the last, each discovery raising as many questions as it resolved, the answers always seeming to retreat just beyond the current reach of the technology. Which is perhaps the most honest description of what science actually is, not a ladder climbed smoothly toward a summit, but a path through fog where each step reveals a little more ground and a little more fog beyond it. The people who walked that path were not mythic figures. They were people who spent long nights in cold laboratories, who argued with each other at conferences, who made mistakes and corrected them, who sometimes followed wrong ideas for years before finding the right ones. Cockcroft and Wharton crouching in a lead-lined hut to look at flashes of light. Lawrence sketching spirals on paper in a Berkeley corridor. The unnamed engineers who stayed up through the night when a magnet failed or a vacuum seal cracked. The history of the accelerator is also the history of patience, of people willing to build something that might not work for an answer that might not come in their lifetime. It is a kind of faith, though not a religious one, a faith that the question is worth asking, that the universe has an answer, that if you build the machine precisely enough and run it long enough and look carefully enough at what comes out, the structure beneath the structure will eventually show itself. For a long time, the proton was thought to be a fundamental particle, indivisible. A point of matter with a positive charge, one of the two building blocks of the atomic nucleus alongside the neutron. It was small, roughly 1 femtometer across, which is 1/millionth of a billionth of a meter, but it was assumed to be solid and featureless all the way down, the way a billiard ball is solid. That assumption was wrong. The evidence came in the late 1960s from a series of experiments conducted at the Stanford Linear Accelerator Center in California. The experiments were called deep inelastic scattering. The name is precise, deep, because the electrons were fired with enough energy to penetrate deep into the proton rather than simply bouncing off its surface. Inelastic, because the collisions were not the gentle, energy-preserving kind, but violent enough to break things apart. Scattering, because the electrons were deflected, and the pattern of deflection was the data. Here is the principle. If you fire a small, fast object at something soft and uniform, a ball of putty, say, It will deflect gradually and predictably, spreading out in a smooth pattern. But if the object you're firing at contains hard, dense interior structures, small lumps, point-like concentrations of mass, then some of your projectiles will deflect sharply, bouncing back at large angles that a smooth, uniform target could never produce. Rutherford had used exactly this logic in 1911, firing alpha particles at gold foil and finding that some bounced nearly straight back, which told him that the atom contained a small, dense nucleus. Now, 50 years later, the same logic was being applied one level deeper. When physicists at Stanford fired high-energy electrons at protons and measured the angles at which they scattered, they found that some electrons were deflecting at large angles, far larger than they would if the proton were a smooth, uniform sphere of charge. Something inside the proton was hard and point-like. Something was deflecting those electrons sharply. The proton had internal structure. The things doing the deflecting came to be called quarks, a name borrowed by the physicist Murray Gell, man from a line in James Joyce's Finnegan's Wake, which contains the phrase 3 quarks for muster mark. The choice of name was perhaps a little whimsical, but the particles themselves were anything but. Quarks are, as far as we can tell, genuinely fundamental. Not made of anything smaller, not composite objects in the way the proton is composite. They are point particles, like electrons, with no measurable internal structure, even at the finest scales we can probe. Inside an ordinary proton, there are 3 quarks. 2 of them are called up quarks, and 1 is called a down quark. These names, up and down, are not spatial descriptions. They are labels for a property called isospin, which is an abstract quantum characteristic. What matters physically is this. Up quarks carry an electric charge of positive 2/3, and down quarks carry a charge of negative 1/3. 2 up quarks plus 1 down quark gives a total charge of 2/3 plus 2/3 minus 1/3, which equals 1. A proton has a charge of exactly 1. The arithmetic works out precisely, which is one of the first signs that the quark model is not an approximation, but something real. A neutron, for comparison, contains 1 up quark and 2 down quarks, 1 charge of positive 2/3 plus 2 charges of negative 1/3 each. 2/3 minus 2/3 equals 0. The neutron is electrically neutral. Again, the arithmetic is exact. But what holds the quarks together inside the proton? This is where a new force enters the story. A force that is, in some ways, the most remarkable of the 4 fundamental forces of nature. The force is called the strong nuclear force, and its job is to bind quarks together. It is carried by particles called gluons, named for the fact that they glue quarks together. Gluons are massless, like photons, and they move at the speed of light. When a quark emits or absorbs a gluon, the strong force is being exerted. In this sense, gluons are to the strong force what photons are to electromagnetism, the messenger particles, the carriers of the interaction. But the strong force behaves in a way that has no analogy in everyday experience, and it is worth taking the time to understand why, because it leads to one of the strangest facts in all of physics. Gravity and electromagnetism both weaken with distance. The further apart 2 masses or 2 charges are, the weaker the force between them. This is intuitive. It matches everything we observe in the large-scale world. The strong force does not behave this way. At very short distances, within the proton, where quarks are close together, the strong force is relatively weak, allowing the quarks to move somewhat freely. This property is called asymptotic freedom, meaning that at very high energies and very short distances, quarks behave almost as if they were free particles. But as you try to pull 2 quarks apart, as the distance between them increases, the strong force does not diminish. It stays roughly constant or even grows slightly. It is as if the quarks were connected by a rubber band that gets harder to stretch the more you pull it rather than easier. The reason for this is buried in the mathematics of the strong force, but there is a physical picture that helps. Gluons, unlike photons, interact with each other. Photons, the carriers of electromagnetism, do not attract or repel each other. They pass through each other without interaction. But gluons carry something called color charge, which is the strong force equivalent of electric charge, and gluons interact with other gluons that also carry color charge. This means that the field lines of the strong force, the lines along which the force acts, do not spread out in all directions the way electric field lines do. They are pinched together into a narrow tube, a flux tube, between the quarks. The energy stored in this tube is roughly constant per unit length, which means that as you pull the quarks further apart, you are not weakening the force, but stretching the tube, and the energy required grows linearly with distance. And here is the consequence that stops you in your tracks. If you try to pull a quark out of a proton, if you pour enough energy in to stretch that flux tube to its limit, the tube does not simply snap and release a free quark. Instead, the energy you've put in is enough to create a new quark-antiquark pair from the vacuum. The tube breaks, but at the break point, two new quarks appear, one at each end of the break, and you end up with two bound systems instead of one free quark. Every time you try to liberate a quark, you create more quarks instead. No matter how much energy you apply, you cannot isolate a single quark in empty space. This is called confinement. Quarks are permanently confined within particles called hadrons, a category that includes protons, neutrons, and the many other composite particles made of quarks. A free quark has never been observed in any experiment, anywhere, at any energy. Every quark ever detected has been detected indirectly through its effects on the particles around it, while it was bound inside a hadron. Confinement is not a failure of our technology. It is a feature of the strong force itself. What this means for the proton is that it is a deeply strange object. It is not a hard sphere. It is a seething, dynamic system. Inside the proton, the three quarks, the two up quarks and one down quark, are constantly exchanging gluons, and those gluons are constantly fluctuating, splitting briefly into quark-antiquark pairs that almost immediately annihilate again. The interior of the proton is a churning sea of virtual quarks and gluons, flickering in and out of existence on timescales so short they cannot be directly observed. The three so-called valence quarks, the ones that give the proton its identity, are embedded in this sea, not sitting still but moving rapidly, held by the constant exchange of gluons. In fact, if you were to ask how much of the proton's mass comes from the rest mass of its three quarks, the answer is surprising. The up and down quarks are very light. Together, the three quarks account for only about 1% of the proton's total mass. The remaining 99% comes from the energy of the gluon field, from the kinetic energy of the quarks moving around, from the ceaseless activity of the interior. The proton's mass is almost entirely the energy of the forces holding it together. Most of the mass of everything you have ever touched, your own body, the chair you're resting in, every object you have ever held, is not the mass of quarks. It is the energy of the strong force, frozen into matter. It is, in a very real sense, made of motion. This is the level of reality that particle accelerators are designed to probe, not the proton as a whole, but the quarks and gluons inside it, the dynamics of the strong force, the strange and permanent confinement that means the most fundamental building blocks of matter are never found alone. To see them at all, you have to smash the proton open and read the wreckage, which is precisely what happens next. There is a moment, lasting far less than a trillionth of a second, when two protons meet inside the LHC and the universe briefly becomes something it almost never is. Let's stay with that moment. The two protons have been circling the ring in opposite directions, each carrying 6.5 tera-electron-volts of energy. As they approach the crossing point, focusing magnets squeeze the beams down to a width of about 16 micrometers, roughly a fifth of the width of a human hair. The bunches pass through each other, and somewhere in that crossing, two protons come close enough that their constituent quarks and gluons interact directly. What actually collides is not, strictly speaking, the proton as a whole. It is one of the quarks or gluons inside one proton interacting with one of the quarks or gluons inside the other. The remainder of each proton, the other quarks, the gluon field, continues forward, slightly disrupted, and eventually produces a spray of particles in the forward direction that detectors must account for. And what happens in that hard collision is something that sits at the heart of Einstein's understanding of the universe. Energy and mass are not two different things. They are two aspects of the same thing. Mass is a form of energy, and energy can condense into mass. The relationship between them involves the speed of light, a very large number, which means that a small amount of mass corresponds to an enormous amount of energy, and conversely, that creating mass requires an enormous concentration of energy. This is why the LHC must push its protons to such extraordinary energies before the collisions become interesting. Creating new, heavy particles requires enough energy to pay for their mass. In a collision at the LHC, the combined energy of the two protons, 13 teraelectron-volts in total, is available to be converted into new particles. Not all of it goes into the hard collision, much of it is carried away by the proton remnants. But the portion that does go into the hard collision can create particles far heavier than the protons themselves. A proton has a mass of about 938 million electron volts, roughly 1 giga-electron volt. Particles created in LHC collisions can have masses of hundreds of giga-electron volts, or even thousands. They are created from pure energy, condensing briefly into matter. The word briefly deserves emphasis. The particles created in a high-energy collision are not stable. They exist for extraordinary short periods of time before decaying into lighter, more stable particles. The timescales involved are so small that ordinary language struggles with them. A particle might exist for a femtosecond, 1/millionth of a billionth of a second. Another might exist for an attosecond, 1,000th of a femtosecond. Some particles exist for such a short time that even traveling at close to the speed of light, they move only a fraction of a millimeter before they decay. Others are so short-lived that they decay before they can travel any measurable distance at all and can only be inferred from the particles they produce. Let us take a specific example, because concrete cases make abstract ideas real. In 1995, physicists at Fermilab in Illinois, working with a large synchrotron called the tevatron, announced the discovery of the top quark. The top quark is the heaviest of the 6 varieties of quark that are known to exist. Its mass is approximately 173 gigaelectron volts, that is, 173,000 million electron volts, or roughly 184 times the mass of a proton. It is heavier than an entire atom of gold. It is, in fact, the heaviest known fundamental particle, and its mass is so large that it dwarfs everything else in the quark family. The top quark does not exist in ordinary matter. It cannot. Its lifetime is extraordinarily brief, about 5 times 10 to the minus 25 seconds, which is less than a trillionth of a second. This is actually shorter than the timescale on which the strong force normally operates, which means the top quark decays before it can even form a bound state with another quark. It is created in a collision, exists for an instant as a genuine particle in its own right, and then decays, almost always into a bottom quark and a W boson, which then decay further. The top quark's existence is inferred entirely from the particles it leaves behind. To produce a top quark, you need enough energy to pay for its mass. At Fermilab, the tevatron was colliding protons with antiprotons, the antimatter counterpart of the proton, identical in mass but opposite in charge, at energies of about 1.8 teraelectron volts. This was just barely enough to produce top quarks, and they appeared rarely, requiring the analysis of millions of collisions to accumulate enough examples to be confident of the discovery. The announcement in 1995 came after years of data collection and careful analysis by two large experimental teams, CDF and D0, working at the same machine, independently, cross-checking each other's results. What does a collision actually look like in terms of what the detector sees? Not a single clean event, a cascade. When two protons collide at high energy, the products of the collision, the new particles created from the energy, are themselves often unstable, and they immediately begin to decay. Those decay products may also be unstable, and they decay further. The result is a shower, or in some cases several showers, of particles spraying outward from the collision point in all directions. A typical high-energy collision at the LHC produces hundreds of particles simultaneously. They fan out through the detector, each one following a curved path in the magnetic field that permeates the detector volume. The curvature of each track encodes information. A particle with a large electric charge curves more sharply. A particle with high momentum curves less. By measuring the radius of curvature, you can calculate the particle's momentum. By knowing its charge, inferred from the direction of the curve, since positive and negative charges curve opposite ways in the same field, you can identify its charge. From there, additional measurements in other detector layers allow you to determine its energy and, combining momentum and energy, its mass. No two types of fundamental particle have the same mass. The collision point itself, seen from the detector's perspective, is a small region of extraordinary violence and creation. Particles condensing from energy, existing briefly, decaying, their daughters decaying in turn, the whole cascade unfolding in a volume smaller than a grain of sand, in a time shorter than any human instrument can directly measure. What the detector captures is not the event itself, but its aftermath, the trails left by the stable or long-lived particles that eventually reach the detector layers and deposit their energy there. There is something almost philosophical about this. The most interesting particles, the heaviest, the rarest, the ones that might tell us something new, are the ones that exist for the least time. They are the most fleeting. They leave the least direct evidence. They must be reconstructed from inference, from the careful analysis of what they became rather than what they were. The universe makes its secrets brief, and physicists must be patient detectives, reading the evidence of things that no longer exist. This is the moment of creation and the moment of dissolution, compressed into a single event, energy becoming matter, becoming energy again, in the time it takes light to cross the width of a proton. And in that passage, if you are watching carefully enough, with instruments sensitive enough, you can read what the universe is made of. A particle detector is, at its heart, a machine for reading clues. The particles produced in a collision are invisible, not in the colloquial sense of being too small to see, but in the literal sense that most of them do not interact with light in any way that makes them visible to the eye. They pass through air, through glass, through human tissue, without leaving any trace a human could perceive. The detector's job is to make them leave a trace in something, in a medium that responds to their passage in a measurable way. The detectors at the LHC, the two largest, are called ATLAS and CMS, which stand for the toroidal LHC apparatus and compact muon, solenoid respectively, are both enormous. ATLAS is 46 meters long and 25 meters in diameter, roughly the size of a 5-story building lying on its side. CMS is more compact but denser and heavier, weighing about 14,000 tons, more than twice the weight of the Eiffel Tower. Both detectors are built around the collision point, surrounding it on all sides, so that particles flying outward in any direction will pass through at least some of the detector's layers. The architecture of both detectors follows the same general logic, built-in concentric layers like the rings of a tree, each layer designed to capture different information from different types of particles. The innermost layer, closest to the collision point, is the tracker. The tracker is filled with fine-grained silicon sensors, the same basic technology used in the image sensors of digital cameras, but engineered to extreme precision. When a charged particle passes through a silicon sensor, it knocks electrons free from the silicon atoms, creating a tiny electrical signal. By reading these signals across millions of tiny sensor elements, the tracker can reconstruct the path that the particle took as it curved through the magnetic field that permeates the tracker volume. The magnetic field in the tracker is produced by a large superconducting solenoid, a solenoid being a coil of wire-carrying current which produces a uniform magnetic field along its axis. In CMS, this solenoid produces a field of 4 Tesla, nearly 80,000 times stronger than Earth's magnetic field, filling the entire inner detector volume. A charged particle entering this field curves. The radius of curvature depends on the particle's momentum and charge. High momentum particles curve gently, low momentum particles curve tightly. Positive charges curve one way. Negative charges curve the other. By measuring the curvature precisely, and the tracker can measure particle positions to a precision of tens of micrometers, a fraction of the width of a human hair, physicists can determine both the sign of the charge and the magnitude of the momentum. Beyond the tracker lies the calorimeter system. Calorimeters. The name comes from the Latin for heat, calorimeter meaning heat measurer, work on a different principle. Instead of letting particles pass through and simply recording their positions, calorimeters stop the particles. They are made of dense material, lead, iron, tungsten, or crystals of lead, tungstate, in which particles interact and lose their energy through a cascade process called a shower. When a high-energy electron or photon enters the electromagnetic calorimeter, it begins to interact with the dense material. An electron loses energy by emitting photons. Each photon creates an electron-positron pair, a positron being the antimatter counterpart of the electron, identical in mass but opposite in charge. Each of those particles loses energy by emitting more photons. The cascade multiplies. 1 particle becomes 2, 2 become 4, 4 become 8, and so on, until all the particles in the shower have lost enough energy that they are absorbed. The total amount of light or electrical signal produced by the shower is proportional to the energy of the original particle. By measuring the shower, you measure the energy. The hadronic calorimeter, the outer layer of the calorimeter system, works similarly but for hadrons, particles made of quarks, like protons, neutrons, and pions. Hadrons interact with matter primarily through the strong force, and their showers are larger and less regular than electromagnetic showers, requiring more material to contain them. The hadronic calorimeter is accordingly thicker, denser, and less precise in its energy measurement, but it captures the bulk of the energy carried by the strongly interacting particles. After passing through the calorimeters, most particles have deposited all of their energy and are absorbed, but one type of particle punches through everything, the muon. A particle like the electron, but about 207 times heavier, interacts only weakly with matter. It does not shower in the calorimeters. It passes through meters of steel as if it were barely there, leaving only a faint ionization trail. The outermost layer of the detector is the muon system, designed specifically to catch these penetrating particles. It consists of large chambers of gas through which muons pass, ionizing the gas and creating electrical signals that mark their trajectories. The identity of a particle is never directly observed. It is inferred. An electron, for example, leaves a curved track in the tracker and deposits all its energy in the electromagnetic calorimeter, leaving nothing in the hadronic calorimeter and nothing in the muon system. A muon leaves a curved track in the tracker, minimal energy in the calorimeters, and a clear signal in the muon chambers. A neutron, being electrically neutral, leaves no track in the tracker at all, deposits energy in the hadronic calorimeter, and leaves nothing in the muon system. A photon leaves no track but deposits energy in the electromagnetic calorimeter. Each particle has a signature, a characteristic pattern of signals across the detector layers, and the process of identifying particles is the process of matching observed patterns to known signatures. Now consider the data challenge this creates. The LHC produces roughly 40 million bunch crossings per second. Each crossing can contain dozens of individual proton collisions. Each collision produces hundreds of particles. Each particle leaves signals in millions of sensor channels. The raw data rate from a detector like Atlas or CMS, if everything were recorded, would be roughly 1 petabyte per second, 1,000,000 gigabytes every second. No storage system on Earth could handle this. The solution is a trigger system, an electronic filter that operates in real time, making decisions in microseconds about which collisions are interesting enough to keep. The first level of the trigger is implemented entirely in custom electronic hardware, operating so fast that it must process events faster than the signals from the detector can be read out. It looks for crude signatures of interesting events, large energy deposits, pairs of muons, missing energy, which indicates a particle that passed through without interacting, like a neutrino or, potentially, a dark matter particle. Events that pass this first filter are passed to a second level, implemented in software running on a large computing farm, which performs a more detailed analysis and makes a final decision. Of the 40 million crossings per second, only about 1,000 are ultimately written to permanent storage. The rest are discarded forever in real time by algorithms making decisions in microseconds. This is a profound act of curation. The physicists who design the trigger are deciding, in advance, what kinds of events are worth saving. They are making a bet about what new physics might look like and building that bet into the electronics. An event that passes through the filter but doesn't match any expected signature might be discarded, its secrets lost. This is one of the deeper challenges of experimental particle physics. You must know enough about what you're looking for to design a trigger that will catch it. But if you knew exactly what you were looking for, you wouldn't need to look. The data that does survive the trigger is processed by computing grids distributed across dozens of institutions around the world. Thousands of physicists analyze it, looking for patterns, for excesses above expected backgrounds, for the faint statistical signal that says a new particle has been produced. The discovery of the Higgs boson in 2012, which we will come to shortly, required the analysis of quadrillions of collisions, searching for a signal that appeared in only a handful of events per million, a whisper against an enormous roar of background. This is what it means to read the wreckage. Not simply to look at what happened, but to reconstruct, from signals in silicon and gas and crystal, the brief lives of particles that no longer exist, particles that were born and died in less time than it takes light to cross an atom. The detectors are monuments to human ingenuity and to a particular kind of patience. The patience of people who are willing to build instruments of extraordinary complexity to catch the faintest possible signal of something they have never seen before. There is a table. It fits on a single page. It contains a small number of entries, a few dozen depending on how you count, and it describes with extraordinary precision every particle and every force that has ever been directly observed in any experiment anywhere in the world. It is called the Standard Model of Particle Physics, and it is the most successful scientific theory ever constructed. Not the most famous, perhaps, and not the most elegant, by some tastes. But in terms of the accuracy with which its predictions match experimental measurements, nothing else comes close. The Standard Model was not built in a day or by a single person. It emerged over roughly 2 decades, from the late 1960s through the mid-1970s, as a synthesis of theoretical work by many physicists and experimental confirmation from many accelerators. Its architecture is worth understanding, because the architecture is itself a kind of revelation about the structure of nature. At the foundation of the Standard Model are two families of fundamental particles, quarks and leptons. Quarks, as we have already explored, are the constituents of protons, neutrons, and all the other particles that feel the strong force. There are 6 varieties, or flavors as physicists call them: up, down, charm, strange, top, and bottom. They come in pairs, arranged in 3 generations. The first generation, up and down, makes up ordinary matter. The second and third generations, charm and strange, top and bottom, are heavier versions, unstable, produced only in high-energy collisions and decaying quickly back to first-generation particles. Why there are 3 generations and not 2 or 4 or 17 is a question the Standard Model accommodates but does not explain. It is simply what the experiments found. Leptons are the other family of matter particles. The electron is a lepton, so is the muon, the heavier, unstable cousin of the electron that passes through detector walls, and so is the tau particle, heavier still. Each of these charged leptons is accompanied by a corresponding neutrino: the electron neutrino, the muon neutrino, the muon neutrino, the muon neutrino. Neutrinos are electrically neutral, almost massless, though not quite massless, as we will discuss, and they interact so weakly with matter that they pass through the Earth almost entirely unimpeded. Billions of neutrinos from the Sun pass through your body every second. You cannot feel them. They leave no trace. So the matter particles are 12 in total, 6 quarks and 6 leptons, arranged in 3 generations. Every piece of ordinary matter is made from the first generation, up quarks, down quarks, and electrons. The rest are transient visitors, produced in energetic events and quickly gone. Then there are the force carriers. In the Standard Model, forces are not mysterious actions at a distance. They are mediated by particles, messenger particles that are exchanged between matter particles and carry the force between them. The photon carries electromagnetism. It is massless, travels at the speed of light, and has an infinite range, which is why you can see stars from enormous distances. The gluon carries the strong force. There are 8 distinct types of gluon, carrying the color charge we discussed earlier, and their range is effectively limited to the interior of hadrons by the confinement mechanism. The W and Z bosons carry the weak force, the force responsible for certain types of radioactive decay, for the process that makes the sun burn, for the transmutation of one quark flavor into another. The W boson comes in 2 varieties, positive and negative, while the Z is neutral. They are heavy particles. The W has a mass of about 80 gigaelectronvolts, the Z about 91, which is why the weak force has such a short range. Heavy force carriers cannot travel far before their energy is exhausted. And then there is the Higgs boson. It sits in the Standard Model as something slightly different from the others. Not a force carrier in the conventional sense, but the particle associated with a field that permeates all of space and gives certain particles their mass. The idea of the Higgs field was proposed in 1964, independently by several physicists, Peter Higgs in Edinburgh being the one whose name the particle ultimately bore. The problem it was designed to solve was this: the mathematics of the Standard Model, in its original form, required the W and Z bosons to be massless. But experiments were showing that they were very heavy. Something was wrong. The Higgs mechanism, the idea that there exists a field filling all of space and that particles acquire mass by interacting with this field, resolved the contradiction. Particles that interact strongly with the Higgs field move through it as if through a medium that resists their motion, and this resistance manifests as inertial mass. Particles that don't interact with the field at all, like photons, are massless. The Higgs field is not like other fields in one crucial respect. Most fields have a lowest energy state, where the field value is 0, where the field is, so to speak, at rest. The Higgs field's lowest energy state is not 0. It has a non-zero value everywhere in space, always, even in perfect vacuum. This is called a non-zero vacuum expectation value, and it means that the Higgs field is never truly switched off. It is always present, always interacting with the particles that pass through it. The universe is permanently immersed in the Higgs field, the way a fish is immersed in water. The Higgs boson is the ripple in this field, the particle that appears when the field is disturbed sufficiently. Creating it requires enough energy to excite the field into producing a quantum of vibration, and that energy is enormous. The Higgs boson has a mass of about 125 gigaelectronvolts, roughly 133 times the mass of a proton. Producing it at the LHC requires extraordinary collision energies, and even then it appears rarely, in only about 1 in every 10 billion collisions, because the processes that create it are suppressed by the mathematics of the interaction. The discovery of the Higgs boson was announced at CERN on the 4th of July 2012. It was not a sudden finding. It was the culmination of more than 2 years of data collection, of careful analysis by thousands of physicists in 2 independent experiments, ATLAS and CMS, each checking the other's work, each looking for the same signal in the data. The signal appeared in several different decay channels simultaneously, the Higgs decaying to 2 photons, to 4 leptons, to pairs of W bosons. Each channel told the same story. The mass was consistent across all of them. The statistical significance, a measure of how unlikely the signal was to be a random fluctuation, exceeded 5 sigma. The threshold physicists traditionally require before claiming a discovery, meaning the probability of the signal being a coincidence was less than 1 in 3.5 million. Peter Higgs, then 83 years old, was in the audience at CERN for the announcement. He wept. The Standard Model was, in that moment, complete. Every particle it predicted had been found. Every prediction it made had been confirmed. It was a moment of genuine triumph, the kind that comes rarely in science, the kind that feels, briefly, like an arrival. And yet, the Standard Model, for all its precision, is known to be incomplete. Not wrong. Its predictions remain extraordinarily accurate, but incomplete in ways that physicists understand very well and find deeply troubling. The most immediate problem is gravity. The Standard Model contains no description of gravity. It cannot. Gravity, as described by Einstein's general theory of relativity, is a theory of the geometry of space and time, and incorporating it into the quantum framework of the Standard Model has resisted every attempt for decades. At the energies and scales probed by particle accelerators, gravity is so weak compared to the other forces that it can be entirely ignored, and the Standard Model works perfectly well without it. But this cannot be the final state of affairs. A complete theory of nature must include gravity. Then there is dark matter. This dark matter appears to make up about 27% of the total energy content of the universe, compared to the 5% made up of ordinary matter, the matter described by the Standard Model. The Standard Model contains no candidate for dark matter. And there is the matter, antimatter asymmetry. When energy condenses into matter, it should, according to the Standard Model, produce equal amounts of matter and antimatter. The Big Bang should have produced a perfectly balanced universe of matter and antimatter, which would have annihilated each other entirely, leaving nothing but radiation. And yet here we are. The universe is made of matter. Somewhere in the early universe, a slight imbalance arose. A tiny excess of matter over antimatter, roughly 1 extra matter particle for every billion matter, antimatter pairs, and from that excess, everything we see was made. The Standard Model cannot fully account for this asymmetry. It contains some violation of the matter, antimatter symmetry, but not nearly enough to explain the universe we observe. The Standard Model is a map. It is an extraordinarily accurate and detailed map covering enormous territory. But it is not the territory. There are regions beyond its edges, marked, as old cartographers used to write, with the suggestion that something unknown lies there. And the machines are still running, still listening, still looking for what lies beyond the map's edge. In a large building on the Fermilab campus in Illinois, a ring of magnets sits in a specially climate-controlled room. The ring is about 14 meters across, modest by LHC standards, almost intimate. Inside it, a stream of particles called muons circulates in a magnetic field, and the experiment watching them is called muon G2. It has been one of the most carefully observed experiments in physics over the past several years, and what it is listening for is very quiet indeed. A muon, as we have noted, is like an electron but heavier. It has a magnetic moment, meaning it behaves like a tiny magnet with a north and south pole oriented along its spin axis. In a magnetic field, this tiny magnet precesses. It wobbles the way a spinning top wobbles when it's not quite vertical, slowly rotating around the direction of the field. It depends on a quantity called G, the gyromagnetic ratio, and the standard model predicts that G is very slightly larger than 2. The small extra amount coming from the muon's interactions with the quantum fields that fill the vacuum, including virtual particles that briefly flicker into existence and influence the muon's magnetic properties. Measuring G with extreme precision and comparing it to the standard model prediction is a way of asking whether the standard model has captured everything. If there are particles or forces beyond the standard model, particles too heavy or too weakly interacting to have been directly produced at current accelerators, they would still contribute to the muon's wobble through these same virtual quantum effects. Their contribution would be tiny, but it would show up as a small discrepancy between the measured value of G and the predicted value. The experiment is, in essence, using the muon as a delicate antenna, listening for signals from physics that has not yet been discovered. For years, there was a tantalizing hint. The Brookhaven National Laboratory in New York had measured G in the early 2000s and found a value slightly higher than the standard model predicted, a discrepancy of about 3.5 sigma, which is statistically suggestive but not conclusive. Fermilab built a new experiment to check this, using a more intense muon beam and more precise measurement techniques. The experimental ring was actually transported from Brookhaven to Fermilab in 2013, a remarkable journey in itself. The 14-meter ring moved in one piece on a specially constructed truck, traveling by road through the night, crossing state lines, arriving intact. The Fermilab results came in stages over several years, each announcement adding more data and more precision. And in June 2025, the final results were announced, achieving a precision of 127 parts per billion, a measurement of extraordinary delicacy. The result agreed closely with a revised standard model prediction that theorists had refined substantially in the intervening years. The earlier discrepancy, while not entirely gone, was significantly reduced. The whisper of new physics had become quieter. This is not a failure. This is how science works. The experiment succeeded magnificently in what it set out to do, measure something with unprecedented precision. The fact that the measurement agrees with the standard model is itself information. It tells us that whatever lies beyond a standard model does not strongly affect the muon's magnetic moment, which constrains what that new physics can be. The universe answered a question, and the answer was, not here, not in this way, which tells you where not to look next, and that is genuinely useful. The searches at the LHC itself continue. Run. 3 of the LHC, operating at 13.6 tera-electron volts, a new record set in July 2022, is collecting data, and physicists are sifting through it for signs of particles not in the standard model. They are looking for supersymmetric particles, partners to the known particles, predicted by a theoretical framework called supersymmetry, which would extend the standard model and could explain dark matter. They are looking for extra dimensions of space. They are looking for signs of new forces. So far, none of these searches have found what they were hoping for. The standard model continues to hold. But the searches continue because the questions are real. Dark matter exists. The matter-antimatter asymmetry exists. Gravity exists and must eventually be reconciled with quantum mechanics. These are not theoretical puzzles that physicists have invented for themselves. They are features of the universe that demand explanation, and the current framework cannot provide them. The future of the field lies, in part, in larger machines. CERN has been developing plans for a future circular collider, a machine with a circumference of nearly 100 kilometers, more than 3 times the size of the LHC, buried in a new tunnel beneath the French-Swiss countryside. Such a machine could reach energies roughly 10 times higher than the LHC, opening up regions of the mass spectrum that are currently beyond reach. It would be an extraordinary undertaking, larger and more expensive than any scientific instrument yet built, requiring international collaboration on an unprecedented scale. And yet even this would fall short of a particular horizon that physicists sometimes contemplate with a mixture of wonder and humility. There is a scale of energy, called the Planck scale, after the physicist Max Planck, at which gravity and quantum mechanics are expected to finally meet, where the 2 great frameworks of 20th century physics would need to be reconciled into a single theory. The energy required to probe this scale directly is so vast that an accelerator built to reach it would need to be larger than 10 times the diameter of the Sun. That is not a machine that will ever be built. The Planck scale is, in a practical sense, forever beyond the reach of direct experiment. Whatever theory eventually unifies gravity with quantum mechanics will have to be tested in other ways, through cosmological observations, through indirect measurements, through mathematics whose predictions can be checked against nature in subtler fashion. This is a strange position to be in. Physicists are in possession of the most precise and successful scientific theory ever constructed, and they know it is incomplete. They are building the largest and most complex machines in human history, and they know those machines will not reach the scale where the deepest questions live. They are listening for signals from physics they cannot yet see, with instruments of extraordinary sensitivity, and the signals have not yet come. And yet, the enterprise continues. It continues because the questions are worth asking, even when the answers are slow. It continues because every partial answer, every new particle found, every discrepancy measured, every prediction confirmed or refuted adds to a body of knowledge that is genuinely cumulative, genuinely growing. The standard model itself was built from decades of such partial answers, each one seeming insufficient at the time, each one contributing to something that eventually cohered into a framework of extraordinary power. There is something else worth sitting with, quietly, as the night deepens. The quarks and electrons that particle accelerators study are not remote things. They are not the concern of specialists in distant laboratories, separate from ordinary life. They are you. The matter in your body, the carbon in your cells, the oxygen in your blood, the calcium in your bones is made of atoms, and those atoms are made of protons and neutrons, and those protons and neutrons are made of up quarks and down quarks, bound together by gluons carrying the strong force. The electrons orbiting those nuclei are held there by photons carrying the electromagnetic force. The radioactive decay that made certain elements in stars and spread them into space before the solar system formed was governed by the W boson carrying the weak force. Every force in the standard model is present in your body, operating at this moment, holding you together. The Higgs field that fills all of space is passing through you right now. The quarks in your protons are exchanging gluons right now, in the same way that quarks exchange gluons in the LHC's collision products, in the same way they have exchanged gluons since the first protons formed, a fraction of a second after the Big Bang. The physics being studied in those cold tunnels beneath the French-Swiss countryside is not abstract. It is the physics of what you are. And the atoms in your body, The carbon and oxygen and hydrogen were forged in the cores of stars that lived and died before the sun was born. The protons in those atoms have been protons for nearly 14 billion years, since the universe cooled enough for quarks to be confined. They have been part of gas clouds, of stars, of planets, of oceans, of living things, and now of you, the same quarks, the same electrons, the same forces. What the machines at CERN are searching for is not something alien to us. They are searching for the rules of the thing we are made of. They are asking, with extraordinary care and precision, what it means to exist at all, what the ground beneath the ground beneath the ground turns out to be. That question has no final answer yet. Perhaps it never will. But the asking of it, the patient, careful, precise asking of it in tunnels and detector halls and computing centers spread across the world is one of the most quietly remarkable things that human beings have ever done. It is enough to wonder at it. You don't have to hold it all. Just let it settle the way understanding sometimes does, not all at once but slowly over time in the dark. The machines are still running beneath the earth tonight, cold and patient and precise, asking their question in the only language the universe answers, and somewhere in the data perhaps the next piece of the answer is already waiting to be found. And so we leave it there. Somewhere behind you, the day has grown very distant. The tunnel is quiet, the protons are circling, the cold is holding everything in place. Drift now, if you're ready. Sleep well.